Okay, we're live. Great.
All right, Mary, we're ready when you are.
Okay, so the first thing that we're going to start off with is the electricity and magnetism. I think it's a bit further back in your binder. I don't think they go in order. So all the lessons that are in your binder are the general format for how the slides were created, but there are some differences. So if you like what you see on the slide, you can kind of follow that verbatim. If you want to read over the lessons and do some of the additional things that are there, then that's up to you as well. Okay, so what we're going to do is look at static electricity a little bit and think about why hair will stand up when you take off a hat. Before we get into that, do you have any ideas? We want to kind of get the girls starting to think about these big overlying questions. So any ideas you want to share? Static electricity, hair, getting shocked when you open up the door. Okay. Well, I'm sure they would be sharing a lot of things that they know. You could start off with asking questions. Have you ever shocked yourself? Have you ever walked on carpet, touched a doorknob, anything like that? So there are three kind of introductory stations to kind of get them thinking about things at the beginning. One of them is static electricity interactive. The second is with balloons, rubbing some cloth over them, trying to pick up some paper dots. And the third is styrofoam plates, rubbing some cloth on them again, trying to pick up another plate. So what we're going to do is give you about 10 minutes right now, and then we want you to explore these in any pattern that you want. The materials for the balloon and the styrofoam, well, those would be separate. So for the balloon, so you pick up a balloon, blow it up, tie it. You will be using these for a later activity, so keep track of it. There are some paper dots in here. You can cut your own if needed. And then there's some paper or styrofoam plates. And again, with some basic directions here. Okay? So please try all three of the activities at any rate. If you want to have a partner, we do have enough supplies for two at minimum.
Okay, so just so that you guys know, the activities that are in the binder are really kind of the most basic part of it. And as people have done this over the past couple of years, people have added, introductory activities and so forth. So what Mary has up here, this is an introductory activity, and so the instructions are on the slide. They are not in your binder, but you have access to the slides. So if you want to do them as they are written, that's fine. They're just kind of stripped down a little bit. It is. I think that Anne has shared a folder.
Yeah, so it should be in the 2019-2020 Stellar Girls file, first of all.
Yep.
Then you should see all the schools listed, and then there should be a separate folder called the Stellar Girls Training.
That's in the main folder.
Although to be perfectly honest, as much as you can over the next 2 days, it is valuable, I think, to kind of place yourself in the position that your students are going to be in, because it gives you an idea of their experience. So, they're not going to have the activities sitting right in front of them on paper unless you choose to print out something and give it to them. So generally, this is what they would see and have to work off of. But it is up to you how you want to run your session. I have high school girls who come and help me, right? Carol and I do our program for the local middle schools, but we're a high school program. And so our high school students look at what's up here on the board, and that's how they help guide our students, right? But you'll have to decide how you want to do it. So when Mary is saying that you should kind of go and explore, she basically is saying, take a look at what's up there, grab the stuff and go kind of play the same way your
Yeah, you're in the
students will
role
play.
of this.
Yes.
The girl right now.
So all
Okay,
the
so please
materials
come
are
up.
up there, go
Again,
and
go in any order, follow directions on the board. Use your, use your notebook to jot down your ideas.
How to bring your notebook? I don't. Bring your notebook. We'll use my notebook. I'll be there.
I'll have those.
I don't know why it's doing that, but I'll just add you.
It might be a different, like their Google account.
Yeah.
So.
Yeah.
Okay.
So the idea of the slide was.
Or you can put it in a separate.
And then
Alright, so I'll talk about
I know,
With our, with a OneDrive, Google Drive, so it's just like, it's a nightmare to figure out when to use. Just a couple of hard drives, but any of them.
No, it does not. The styrofoam is a separate thing. They can be on there, they don't have to be. Yeah, and they're gonna like notice it's not picking up right away. What more is there a difference in the okay, I was like, oh,
It takes 3 days to go.
and then it even gives that challenge of moving from, so you can say, okay, well, once you figure that out, starting here, putting here, which group can do the most for just the blue and transfer them.
Gotcha.
So I was like, They don't have to be on the styrofoam plate.
This is not working. I know how to make it work.
Yeah.
You're here?
Okay, there, y'all just have.
Alright.
And I was like, here, maybe for this. Of course, I don't understand, try it. So
Yeah.
I'll be open to see.
So it's.
Here. Is it working better?
The hair,
Yeah, so this
Not here,
one was,
same number.
once you do, just plug it into.
Yeah,
Look like a hard drive. That's where I set up that. Free hard drive. Things like. Yeah.
Yes, that is the first one. So.
Just because they slept in one time. I slept 12 hours the other day. And my birthday was 12 hours. And I woke up still tired.
Here's your hair.
I just wanted to ask, I know that's but like just seeing the just makes me think, looking at this, I figured the less separated computational physics and stuff can be. Right. But I just wanted to make sure.
I'm sure that it's okay with sharing.
Literally, you should just repel and come right up.
Catching into a like crazy thing.
Yeah, it is. It's like, I don't know why it's not. Am I supposed to hold like this? So that comes down and then you kind of just whatever direction. Hold that. Literally, look at it. No, I've already done it. Oh,
But it's not yet, you gotta rub it. No, because I tried to, you don't have to rub it on there, just rub it on the back. I was trying to get off everything that was on there, if there wasn't.
And then these are easily.
So I understood the science better.
Unless the. Try maybe this.
Oh, it's gonna die. No, but I was gonna, it's a different, it's older.
Well, it specifically says. So, other coding.
Okay, this one is.
Trying to think outside the box.
Well, if you're having any trouble pretending to be working, they're easily Googleable, so you could actually see the results, and then it's not working. Do you guys want to come up to the computer and try the interactive up there? Okay, we're gonna go with about 3 more minutes.
I suspect this.
Okay, so the directions were doing the started on the wall chart. So then the kids can see positive, every object has positive and negative chart. So maybe try
I've got this one moving.
Oh, yeah. Okay, and then what's happening?
I can get this.
Still won't let it come out, collecting all the negatives. And we'll talk about why that happened. Picking up all the negatives. And it's still there.
I'm just gonna
And
carry
it's
it.
obviously the trash and like repel. So it's telling the negative as start. And again, keeping the positives in mind. Now, if you move, and then it also said just move the balloon around and then like let go of it. So we have to work rather than let go.
See if I can get on my computer.
Okay,
Invite
you
me.
see how the new pole.
If you allow me.
So again, it's
Okay.
opposites or attractive. And then they can play around with different charges and it can still do the same thing, just charges. Okay. Yeah, and that's the same slide, and then. Yes. The file or this, it's, should be Celebrate 2019, 2020. And then it should be pool fire.
Oh.
And then it should be one that says Celebrate, it has to do that training.
Okay.
And it'll say, yes, and it'll say, saving it.
So I'm seeing this thinking computational.
I don't have to, if you wanna add yourself.
Yes. And I meant to.
Because I didn't invite you all. Your email.
The less difference between those times.
Yay.
A question or two, the students, you're doing.
Don't worry about bothering.
Okay. I've done that. Enough people that I can now, just to make sure, you know, but really, I think considering last year, you know, probably.
Yeah, so I'll just do it there. Alright, cool.
Try to sit right here.
I'm gonna add your email. My.
So it'll invite you, and then closer.
Just real quick, I talked a little bit about the modeling and simulation practices. If you're using something like this, first of all, you're using a simulation to, or a model to understand the concept. But another thing that you can be doing is running your own experiments. So if you have a couple of things with students saying like, try doing this, try doing this, try doing this, what did you learn? That's another computational thinking bit. But the last thing I wanted to point out, which is
Williams on the email, okay.
really sort of a
Need
low,
Elijah.
really sort of an easy thing to do is with just a couple of questions, you can get into assessing a computational model with this. So you can talk about what sort of assumptions did it make? What is it showing from real life? Because obviously this is simplified, just about every simulation is going to be. So what did they leave out from real life? What did they make more explicit? A lot of the times when you're doing something with students, you're overdoing it, so it makes it really obvious what's happening. You know, what is this doing? What is the simulation doing that isn't quite like real life? Right, and then you end up with something a little bit closer to real life. And so that is when you're talking about assessing a computational model, that's really all you're talking about. They don't have to be evaluating, they don't have to say, well, I think the code's a little bit wrong here, or this doesn't follow this equation. Although if you could, that'd be amazing. But just saying, what's it trying to show us? How is it doing that? You know, much smaller questions, and I think would probably help a lot with the science learning as well, just making it explicit what they're supposed to be learning. But you're also doing a computational thinking practice. It's a little bit of thinking about how it was made, right? Why did they choose that sweater? Why did they choose a balloon? Why did they give you the option of removing a wall? Those are all great computational thinking questions that don't have to require a lot of change to what you're doing. It's a quick win, although I'm not a
So
quick
like
win
what you're
person.
saying is there's the science behind it, and then there's also then the CT component, which is like the design of it. Why was this used?
Right. Yes, it's, again, it's doing what you're already probably doing, but just making some of those things a little bit more explicit. Just getting into as a teacher, if you're using something on a computer, take a moment to think about how that must have been made. And take a moment with your students to talk a little bit about how it must have been made or why they made whatever decisions. Why do you have the option of one balloon or two balloons? Those are sort of the annoying questions that a 4-year-old would ask, but that's exactly what you want to do to kids, is make them explain that sort of thing, or at least think about it. If you have an activity where you're actually doing it with the balloons, and then you're also doing the simulation, you can ask, why is the simulation better? Why is it worse? How are the two things different? I just spent way too much time messing with styrofoam plates trying to get them to do exactly what I wanted them to do. The simulation, it's going to work automatically. There isn't going to be some mystical variable that keeps it from working. So, just wanted to interject.
It's over.
Okay. All right, so can we have any discussion on results? What did you see? Balloon, cloth, dots, plates?
The plate one. So however, we see that it jiggles a little bit, but the falling, is that making the plate fall or the small plate falling on your hand part? What is the?
Well, so when you're rubbing the cloth onto the plate, you're kind of energizing the electrons. And when you put another plate on top of it that has the regular positive and negative charges, it should be able to repel it. So what we should see is it kind of bouncing up, and then you would literally be able to hold, it would hold right under it. Not quite working, I knew, but that's what you should do. And then that same principle with the dots, picking up the paper. So a little explanation then on it. So you want to get their feedback, get them thinking about maybe atoms, the charges, why that's happening, and then okay, so in relationship to the plates or to the balloon in the paper, basically when you're rubbing the material on there with the help of friction, you're energizing those electrons and they're moving away and keeping the positives behind. And then when you take off a hat, for example, that movement of the hat coming off, stripping off those electrons, you're leaving these positive charges on the hair. And then, as we talked with a few, when you have charges, we know that opposites attract and likes will repel. So then here you have your positive charges on each of the strands, and they're repelling each other and then standing up straight. All right, so again, if we pose that question again of what is static electricity, again, rubbing things together, whether it's the hat, whether it's the dots, whether it's a slide, you see that a lot. The electrons are moving from one atom to another, and some atoms get extra electrons. So if some atoms are pulling down these extra electrons, which are negatively charged, we have extra, what would be our overall charge? Extra electrons, but then those extra electrons, which are already negatively charged, it would remain negatively charged. And then if we lose some of those electrons and take away some of those negatives, then we're going to be left over with some positives. Now, in the Google Slides, which if you have it open, you should see at the bottom that there's a little speaker notes, and then there's some things listed in there that help guide on questions to pose or answers that they might give. And again, you can add to that if you make a copy. So here we see some of the charges going in, and we're going to be looking at some of the electrical fields that are created. All right, so here's a video. I just click on the little icon. There we go.
It can strike without warning at any moment. You may be walking across a soft carpet and reaching for the doorknob when suddenly, zap! To understand static electricity, we first need to know a bit about the nature of matter. All matter is made up of atoms that consist of three types of smaller particles: negatively charged electrons, positively charged protons, and neutral neutrons. Normally, the electrons and protons in an atom balance out, which is why most matter you come across is electrically neutral. But electrons are tiny and almost insignificant in mass, and rubbing or friction can give loosely bound electrons enough energy to leave their atoms and attach to others, migrating between different surfaces. When this happens, the first object is left with more protons than electrons and becomes positively charged, while the one with more electrons accumulates a negative charge. This situation is called a charge imbalance, or net charge separation. But nature tends towards balance. So, when one of these newly charged bodies comes into contact with another material, the mobile electrons will take the first chance they get to go where they're most needed, either jumping off the negatively charged object or jumping onto the positively charged one, in an attempt to restore the neutral charge equilibrium. And this quick movement of electrons, called static discharge, is what we recognize as that sudden spark. This process doesn't happen with just any objects. Otherwise, we'd be getting zapped all the time. Conductors like metals and salt water tend to have loosely bound outer electrons, which can easily flow between molecules. On the other hand, insulators like plastics, rubber, and glass have tightly bound electrons that won't readily jump to other atoms. Static buildup is most likely to occur when one of the materials involved is an insulator. When you walk across a rug, electrons from your body will rub off onto it, while the rug's insulating wool will resist losing its own electrons. Although your body and the rug together are still electrically neutral, there is now a charge polarization between the two. And when you reach to touch the doorknob, zap, the metal doorknob's loosely bound electrons pop to your hand to replace the electrons your body has lost. When it happens in your bedroom, it's a minor nuisance. But in the great outdoors, static electricity can be a terrifying, destructive force of nature. In certain conditions, charge separation will occur in clouds. We don't know exactly how this happens. It may have to do with the circulation of water droplets and ice particles within them. Regardless, the charge imbalance is neutralized by being released towards another body, such as a building, the earth, or another cloud in a giant spark that we know as lightning. And just as your fingers can be zapped over and over in the same spot, you better believe that lightning can strike in the same place more than once.
Okay, so they kind of mentioned insulators as a way of kind of holding on to those electrons. Well, we're going to be looking at magnets using different with metals that will release that a little bit more, that create some of your magnetism. So the previous screen had said, what we know about magnets? So you want to kind of pose that question again, get the girls kind of thinking, brainstorming, storing out anything that they know about magnets. Some of the things they might say is that there are positive and negative ends, as well as a north and a south pole. You could even give them some bar magnets, have them put them together. Notice that, you know, when two sides are put together, they might attract each other. If they flip one side over, maybe they repel. All right, magnets have invisible magnetic fields, which attract and affect certain metals. Magnetic field lines travel from north to south. It's an invisible field. We're going to be creating that with some iron filings. When you use an electromagnetic field over some kind of magnetic material or metal material, on the right side, left side, we have the electrons and protons kind of randomly placed, and then as soon as you put an electrical field over that, it lines them up, and then that helps create that magnetism. And we're gonna try making some magnets. So what we're gonna do is get some materials, we're gonna get a nail, we're gonna give you some magnets, and we're gonna see if you can turn that nail into a magnet. How can you possibly make it stronger? And then we're gonna look into using iron filings. You can do this in your journal. Put the magnet down on the thing, and then we have cups of iron filings that you can kind of sprinkle over it and see if you can get some kind of field design, kind of like you've been seeing in the previous, similar to that. And then that will show them that even though we don't see that, putting these iron filings on it, we see that there is a field that is created around that. So again, in your journals, notes, whatever, any of these little activities that we ask, you can label under your drawings there. In the back, we have paper cups and nails. And again, it's probably best at minimum 2, if not more people, but come and grab a cup. We have nails, grab a nail, and then there's a bunch of magnets that are very strong, so we gotta try to separate them. So if you want to come back, get those. This one. Or, you can get more than one if you want. See if that can change.
And I'm so certain that I cannot figure out.
No wires yet.
Oh, hi, I'm back.
Tim's got all my people. She had a giving permission to get on it. I couldn't get on it. Everybody else can go in. Yeah. Online. Well, you put it in different. I didn't remember my level of access.
Use the first part of it. That's mine.
I don't remember, so hopefully I'll just do it.
I can go.
Oh, yeah.
I didn't think it, I don't know what. Okay, thank you. Yeah, I'm not sure what it is.
Oh, what did it?
Oh, it's this activity.
Set on the magnet.
Okay, I lost the search. Would anyone else like to magnetize this nail?
There's so many, like, between evergreen and
I remember you have to line them up.
Oh, yeah.
Are you on your desk? I am, I went on it.
I was hard
How do you unmagnetize it?
You rub it.
Just rub it with your fingers?
Yeah, or you can touch it to another piece of metal, but then all the iron filings will.
Yeah, just keep your magnets away from your computers.
What if it gets stronger if you do it more times? Like I did it 1,
Especially
3, we can collect data. 5, 6, how many swipes? 7.
Yeah, iron filings,
Nine,
keep those away from your
10,
computer.
11,
And the magnets.
12, 13.
Then we'll need a couple of iron cups. How do I demagnetize?
I know.
Seems about the same. Although I guess you would have to quantify like the mass of the iron filings you poured out.
Right, and how
To
many?
see like how much it would pick up, or you could do paper clips and like quantify the
Yeah,
paper
that's
clips.
what I always said.
So it could either be paper clips or the mass of the iron filings you pour out to see how much you can scoop out. Paper clips are easier to
Yeah, and
Yep.
they're more easier quantitative data for like 6th graders that don't have the balance.
Yeah,
And the magnet turns them down.
This is doing a really fine job.
And then think how you can make your nail magnet any stronger, or differences in the magnets you initially do, 1 versus 2 versus 3. Does that improve the strength?
Let me move this backwards.
Tee them up or use the T magnetizer.
Okay, heating.
Yeah, that's how.
Let me move that back. Now.
So go under it, just like the
The
easiest way to do this without making a giant mess is if you do it in a petri dish, so it's contained in the fridge, or a test tube is real nice. So then you just put the magnet underneath it. You put the magnet.
This one.
Yeah. And then it's really strong, so you'll see. Yeah.
Oh, I use scissors.
There's the magnetic field.
Hard sock, right?
Yeah. It's like a monster.
Oh, Harry, Stranger Things.
Yeah.
Oh, I love that.
Ooh.
Make artwork. Oh, that is fun.
Yeah, I
gotta pull it.
Taking years to
I'm nervous.
There. That is cool if you want to play.
I'm gonna be
You want to hold like a Polly Pocket.
Like a poly. Yeah.
Almost have to hold that other side. Ooh, there. Teamwork.
Extreme
It's hard to get to work.
You have
like
to
the
not
materials.
Okay.
I cannot get on.
No, you can feel it.
Of course I'm freaking out because I want to leave. Wow.
Hi, Eva can't get on her Google either.
What, and not very magnetic, is that what you're saying? Okay, so that's something that's gonna happen with the girls. So, one of the questions is, can you make the magnet stronger? So, what did you do the first time? Just kind of, just a little bit like that? Okay, well, what do you think you could do next? If you just rubbed it a little bit, rub it some more, and then see more. Okay. Yeah, and maybe with 2 little blocks, maybe 3.
Oh, maybe
Yeah, so maybe
I can't get the choice.
right.
So maybe it means that
That's the problem, right?
So maybe the paper clips are too heavy too. Paper clips are heavy and shady.
Yes.
So I'm thinking that
Well, not necessarily. Iron filings are pretty heavy.
Well,
Well, just
you
say.
know, wider surface.
Yeah.
Oh,
This is not working.
Okay. Well, here's a question to think about. Are all metals magnetic? So, yeah. So there could be a possibility, maybe there's something with the, I'm assuming these are made out of like steel, which would have iron in it. But if this is made out of something different, because like aluminum is not magnetic, it could be. I'm gonna go,
yeah, that's what I was wondering too. Oh no, because it sticks to the magnet. It sticks to the magnet.
all right, did anyone get a magnetic field? Did anyone experience a magnetic field shown? So, the magnetic field is, it usually runs north to south. So from one end of your magnet to the other, you should literally see like striations of the field moving from north to south, just like our North Pole and South Pole. We have this magnetic field that goes around the Earth. It'd be like this up here a little bit.
Some getting it ready to pull it all of it on top, like a monster. Oh, where's the yeah. Yeah, I saw it pulling off. Iron pulled up.
Try maybe if you can try it with the magnet and see if it's.
Ooh, they're all standing. Look at that.
Or
Whoa.
Or maybe like put the magnet down.
Oh, actually, that's pretty bad.
Yeah, that's the north that end is really stronger. Yeah.
Pretty good. That is, look at how it's standing straight up, like, standing up.
No, the magnet test my nails, just a tiny bit.
Oh.
I gotta get better at it, it's not really, they don't really help.
They fall right off.
And then when you're like, out,
If you see how this.
so I gotta make that.
Okay, we go for about another 2 minutes.
I like it as a, we used to have the high school, oh, it worked really good. And you have to have a good battery.
Chair, can I show you? Chair, what you my purse?
Okay.
That's partly right.
Yeah.
Yeah,
I was it. Yeah.
And then they also buy. You want to do that.
Oh.
That it is. It's, you can use that in already there. Right.
Our hardest thing is not.
Yeah, iron filings in the bag,
Everything's so hard, it's,
Yeah.
you gotta find easier stuff,
Right,
teach
right.
them it.
Right. Some of the lessons do have, notes for younger kids and connections in there.
Okay. Good, good, yeah, these seem to be something that we should be able to do, which is good, and that's where I found. Everything has to be redone for them.
Right.
Alright.
All right, we're going to keep moving along. So we just explored magnets a little bit. Now we're gonna pass in the electricity aspect, or the electromagnetic part. So, an electromagnet is a temporary magnet. It is not a naturally occurring magnet. The magnetic field is made due to electricity flowing through or near it, and the magnetic field will disappear if the current is taken off. So what you guys are gonna do is you're gonna create an electromagnet. So we have the same materials in the back. You're gonna have a large nail. You could use the nails that we just used to make the magnet. That's about a 3-inch nail, but we also have larger, like 6-inch nails. You will need to get some wire, so in the back. And again, I think our supplies really are about maybe groups of 3. So you can grab a black, a green, or a red wire that is 6 feet long. You will also grab a dry cell battery. They're over here, I'll put them on the table. We do only have 4 of those. So again, kind of sharing would be more ideal. Some electrical tape. The instructions are on the next page. You will need to secure the end of the wires to the positive and negative ends there. You will use your iron filings again, and then there are some magnets. So I'm going to go over the directions with you on the next slide. And like I said, you could tweak these directions, make it simpler. Basically, you're gonna take the nail. You are going to start wrapping the insulated wire around it in coils. And it's very important that you don't overlap the wire. So you're gonna slowly make these coils over the nail. You do wanna start and leave about 10 inches or so. I mean, it could be 8, whatever. But leave a little bit left over at the tip. Then you're gonna slowly wrap it around. It can go back over in the opposite direction. But again, you just want the coils to be neatly next to each other, not like randomly over each other that way. And then at the very end, you want to leave again another, 10 or so inches free of the opposite end. Once that is done, number 4, you're going to attach the wires. They've already been cut. It might be something that you'll have to do back in your classroom, maybe ahead of time. The kids could do it. They're not like sharp, so it's not something they would cut themselves, but you'd want to take off the insulated end. Take those wire ends, put one on the positive charge, one on the negative charge. You can use the electrical tape to make sure that they stay on. If you don't want to use the electrical tape, you take the free end of the wire and just kind of wrap it around the coils. And then, yeah, so that's the setup there. And then basically, this again is more exploratory. So that object that you've created is called a solenoid. So you're going to take that coil with the nail inside, the coil wires over it, and you can get a compass that tells you direction north, south, east, and west. And you can kind of move it over it, let them kind of explore and see what happens to the arrow. You can remove the nail from the solenoid, but you still want to keep your coils. And then you can put that over the compass, compare, see what has happened, if anything. You can put the nail back in as well. And then use the solenoid with the nail in or out, put it over paper clips and see how that does. And then we do want to make sure that whenever you're doing an activity, that they're always like labeling the activity that they're doing, that they're putting down their observations, their thoughts, anyway, data tables or not, but that they're always documenting what the process is that they're doing and what they're thinking. And then from those observations, which I will give you about 10 minutes to do, then we're going to come back and then think about different variables that we could change regarding your solenoid. Anything regarding the wires, the number of loops that you did, anything related to that. Okay, questions? All right, so again, everything is on the back table.
Because those 4 batteries, you guys might need to like turn tables around, turn chairs around and work at the same table.
And 2 groups could share one battery, so you can still do it and just share one.
You know what I'm saying? So I feel like the best way to go back to
You two have anybody to work with on this? Okay.
I just didn't want.
You wanna come in?
Either one.
Trade with me?
No, I can see. I have some. I'm just asking. I do. If I didn't want to this ring in my back.
It's fine. I'm not wearing this shirt.
Okay. Oh no. Okay.
I didn't realize it's kind of long.
You know what? I didn't.
I can see me really good.
You're the star today.
I was used to, I taught 6 out of the But when I did it at mostly it's like angry girlfriend. Oh, okay. Because I just had to open. Like.
Are you joining this for you?
I just
Here.
No, I think they're all over here. Oh, wait a minute.
Or you could do it this way.
Oh, okay. Okay.
Just pull it. So, yeah, but I actually like it.
It's more, well, it's very visual, you can see the results.
I like the really the play.
Iron filings for this guy.
Yeah, that's it.
Kind of talk to extract the iron
I don't,
They'll be everywhere.
I don't think that won't make a difference.
Oh, all right.
Yeah, yeah, you can kind of hook it on if need be, or you can get electric.
The wires aren't all like together.
Yeah.
Thursday, like these are something. Friday, Thursday. If I ever had. Well,
Right. No, do they want electrical tape, or do you just want to hook it in?
Ready?
Good job.
Well, yeah, not a lot, but it is moving.
And this is how it was actually first discovered, in the 1700s or whatever.
And that's because of the electrical charge, the opposite is pulling the tracks.
Yeah, and well, it's creating this electrical field, which is kind of like those invisible lines that were on that drawing. And the metal in the compass is being attracted to that, so it's kind of drawing itself towards it. Yeah.
You know, I found like, I wonder if the insulator does something to it, but then it's really hot.
Yeah, that's the only
I
reason
had
why
done it with the copper wire
Yeah.
before, and that's really strong
Yes.
magnetism,
Or
but.
it gets hot.
And it will get hot, so that's why you need.
Well, that's like wire actually,
Yeah.
it's super hot on foil, and so you could actually, it gets hot, my kids don't know better, but I
Yes.
know it makes a great magnet. I've
It
done
would
it.
be good to let them have.
Yeah.
Just get a real small piece and let them
Let her
touch
try
it.
it.
So if you touch this right here.
This is not hot, it has an insulator,
No, I'm saying
it
it's
has the
that
rubber.
hot, they touch that.
This, you know, I think this might get warm, but honestly, when, when I've done the copper wire by yourself, like I said, it got hot. It did, it really, the wire, because we were so tightly,
It wasn't insulated.
yeah, and it was just, like I said, back then it made it
Right,
great.
so as you're
Yeah.
doing this, think of variables, different
Yeah.
things that you could change that might affect
Yeah.
how
And
many.
then here, you could try too, and then we're supposed to pick up paper clips.
Oh, so it's dry.
And then think
Yeah.
about some variables that you can change on this, and then.
You sure?
Yeah, but it's just. I'm jumping.
Alright, so I don't wanna be the above on everything. I'm foggy, sorry. I'm like a little kid in the grocery store. You could strip this off, have it, maybe that would be a little better. And I wonder if we needed the smaller nail, because we would have, thinking of how far. Yeah.
Yeah, so they have to change.
But this is so big compared to, we would have to, yeah, we would have to. Let's redo it, but the problem is, it's so. This wire's like too big to pull it down, I guess, like, that's what I think too. Let's just do some flipping, why don't we get some scissors and see what happens?
We don't have to wrap it.
You do wrap the nail. You're supposed to wrap like this, and then you gotta leave it and pull it in, so you put it on the battery.
That works.
Positive and negative.
Well, see,
Let's try.
But we could,
That's how I
let's
was
use some
wondering.
scissors and strip
you
some of
just
it
kind
off
of cross
and see
them
what
any which way. Now they're still lined up.
like I said, we used to, at the beginning when I used to do this, we actually had our little high school class and their junior honor society.
I'm sorry.
And we're teaching our kids science, so it's really awesome. So we work together with their parents, quite some money in elementary school. And the high school got tons of money. And so they got batteries, they had magnets, we never had.
Did you all play that?
Huh?
Did you play anything?
For us,
Yeah,
yeah.
elementary.
Yeah. You get planning time, don't you?
When I was
Yeah. Oh my gosh, that's crazy. Wow.
It was yesterday.
Well, yeah, well, you guys can't go all day up there. Right, right. See? Like it is strong, this might make them sit more. This is stronger, so tighter is better.
Yeah, and it goes like
Yeah.
smaller.
Yeah, so you can see this is actually stronger. Now,
Takes more power to
like I said, if we did these others, we would have some of this, but then it does get hot. So you can even feel, even holding this, you can feel it somewhat warm even through it. Feel the heat coming from it, and yeah. So like I said, when we did it with just the copper wire, it really got hot. It did.
And then
It was
it's
very
like,
dry.
Yeah, especially with little kids, because I,
Yeah.
they get so excited.
But it was awesome. It really works great with except for copper. It
No,
really does. There you go. You got it. There you go. And you know what, I the other end of the nail. And you might know something about it.
I do need a battery. We had high school.
There you go. It's got the two But I think the end and the other end work kind of better. But I do think the tighter you make your coils, the better off you are. So this end is actually stronger. You know what, I think if we strip it, it will get hot. And then it's gonna
Just this
cost
part.
more. Well, right here?
It's wrap it around all the way around.
use the electrical too, you could secure it, make sure it's touching.
Okay.
You know what I'm saying?
Yeah, but actually,
I
not just that we need to do it.
That's a good extra experiment.
Yeah.
Let's see if we can find
Yeah,
something.
at least they can think of that.
Dire circumstances.
Yes.
For those kids that like to play like me, that would be stripping everything and pulling it apart.
Yeah.
That would be me.
Kids that would tear stuff
I
up.
broke magnets, I broke the thermometers all the time in high school, just because I like the mercury.
What was wrong?
Well, it's split up into balls. It would
Did
make
you
all
put
these.
it on the ground? Oh, you
You
were out there, right?
glass,
It should
the
be.
mercury would make all these little.
It should.
I know, it was really good. I was a bad kid. Bad kid. I needed to take everything apart. My parents would tell me.
I was good, but I was.
But then they would have me fix everything, you know, because I like, I know, I was electric, things back together, put the wires back together on our grills and everything, you know, like the vacuum cleaners, and I don't know how, I didn't take, I broke so many watches trying to figure out how watches work. Yeah,
Wow, that's good.
that was terrible.
No, I think that's good. I don't know.
My bad watch don't have.
I don't know if you, I was about to say, I was experiencing.
They didn't like me taking it apart and just like, I'm trying, but I clicked fix things, and they still
I know
fix
it's
things.
You know, my son.
I probably just go with Tara.
Yeah,
So
I do like,
that's a good thing. I mean, I was just telling you.
I'm not leaving this part.
Yeah.
That just, that would be the only thing that I would.
alright, pull more of this out, so we got more wire,
I'm bringing
so
my
I
dog.
want to wrap that tighter.
Alright, again, we wanna make sure the girls are kind of writing down their thoughts, their ideas, what worked, what didn't. I'll give you about 1 more minute.
We're already done. I should have brought a color room, but I brought my yellow notebook, but
Oh, you.
I have paper if you want to have paper.
Well, I'll
Okay.
different things. I'm just-
And then this we could get online, she found all this stuff online. I couldn't find the video, but I figured it must look under whatever it said. The video they showed about electricity, it wasn't, it doesn't.
Yeah, it's on
But it doesn't go into the video.
I guarantee you, which one is the 20?
Did it? I didn't get it. Where do you click? It didn't go anywhere.
Like you don't have the arrow to play?
Uh-uh.
Oh, you know what we'll have to do, because sometimes it has to do with the format that it's like bumping back and
Okay.
forth. You may have to capture it again. But what
Did it
we'll
work
do-
previously? I didn't get it to work. I tried to.
Oh,
she's my
Oh,
dog.
how did you do that?
Well, I was in
Just got out of
presentation mode.
presentation, yeah.
But
No,
you,
it's not.
yeah,
doesn't work.
sometimes it does that just because you're taking it out of somebody else's.
Yeah, I
You
figured
could just
I could look
Google
up whatever you had it in.
What is
Oh, yeah,
static
that's very
electricity?
easy.
Look at it.
That's what I figured I'd be able
Yeah,
to
most
do.
of the videos that we have on there, they're super, they're
Okay.
TED
Yeah.
Talks or whatever, they're
Yeah.
usually pretty easy to find.
I was saying, I
Go
remember,
in.
we didn't meet last year, but, when I had it a couple, this is my third year, but, I said, you always knew everything. I was like, man, you know all this stuff. I don't
No, I
really-
don't.
I'm just
This is
learning it.
like, this is my most uncomfortable. I mean, both, for both Mary and I.
Yeah.
You know, this is my
Which
most
is why we're
uncomfortable
doing these
topic.
lessons for you guys, because that was what
I have learned like
the feedback was.
huge amount doing
My
Stellar
favorite,
Girls,
yeah.
just
Yeah.
because I'm a biology
Yeah.
teacher, I don't
Yeah.
use this all the
Yeah,
time.
and that's why we're always doing the light stuff.
That's why I like it.
Okay.
And this is also
Right.
part of
And
the
it's
reason
safe
why we
environment.
decided that this was a good
Like if something
training
doesn't work,
because
we'll talk
people are
about
so.
it. Yeah.
So,
Okay.
experiment selection, and which is the
Nobody
section.
likes the section, but it does have to do,
Well,
you know, I mean,
yeah.
this is not
We
as
have to be
intimidating
taught.
when
Yes.
you're
After
actually
school,
like,
yes.
oh, it's not as hard as it looks, the
Right.
directions look terrible.
But
But,
that
you know,
is
once you've done it, you kind of go, oh, this
I know
is
that.
hard.
Yeah,
no. She'll collect.
And it actually be a lot less than all those things I have to.
Oh, yeah.
I have to, I said, you know, and
I
I'm
feel,
like, man.
I actually, this is kind of a.
Yeah, and then we got little kids or environment, we got to slow everything down. I said, because they really, you know, started with their Instagram, you know, there.
There's a
We try to help them.
Yeah. Or okay, can anyone share anything that they noticed? And then they put the solenoid over.
I put, as people were talking, I put some things on the board that people were talking about, so that, you know, you could kind of, these are the things that you guys talked about, not me, you just were asking questions, so.
So what did we notice happening when you moved it over the compass? Okay, we saw the arrow kind of moving around. If you took the nail out of the solenoid, did it still move the compass?
Yes.
Okay, why do you think if you didn't have the metal portion in there, why do you think it was still kind of moving it?
Still enough.
Okay, still enough kind of retained there. Now, did you by chance try doing it a little bit later again and seeing like after time it wore off more? Okay, well, so that's a variable that you could do, is you could test, well, how long will the solenoid without the nail hold that charge and then keep maybe moving that compass? Paper clips, anything with that, any interesting variables?
we kind of use that as maybe our measure of how strong the magnet is, like how many paper clips could it hold? Because you were saying like if you're measuring strength, like how do you show, oh, this one's stronger? So like if this one can hold 3 paper clips up, or this can barely hold 1 paper clip, it's like a way of measuring.
And do you think that if you were measuring it with the 3 paper clips, your design with your coils, you think that would match another group that had 3, or maybe other groups picked up more? Why would that vary? So, as Kathy had mentioned, some of the things that we heard, what if we use different wire, thicker wire, thinner wire? What about the coils? Did anyone count their coils as they were going by?
No, but we thought the smaller nail picked up more than the bigger nail. We thought maybe because the coils are smaller.
Okay.
And when we also stripped back some of the copper more, we were able to pick up three of paper.
Right. So maybe the number of coils was the same on thin versus the bigger one, but because the smaller one had less surface area and they were more crammed in there, it made it more powerful. So then the girls could test, well, how many coils? Would 10 coils versus 50 matter in that? Would the size of the nail matter? Let's say you keep the constant of, okay, 50 coils, but do it on the small versus the large. We have, doesn't matter how much space at the end. So I think that was the wire that you left off that you attached to the battery. So maybe if you did a couple inches versus larger, would that affect it? So what we have up here in the variables is, you know, I don't know what kind of board you have at home or whatever at school, but then you could just kind of jot from them and list all these things, or have the girls go up and write down the variables that they thought about. And then that will lead for them to pick one of those and design their experiment to do that. So again, you're kind of bringing in, you know, a little bit of the engineering and design process of them creating, you know, what the experiment should look like, what the object should look like, the coils, the design. They should think about independent and dependent variable, even at, you know, second, you know, third, fourth grade for sure. They should be exposed to those words and start kind of knowing that. They should create a procedure, maybe a data table to how to track that. And of course, always thinking about their hypothesis. And all of that would be based on this exploration that they did initially. And then that gives them this, you know, background knowledge, and then they can.
For those of you guys who are doing NGSS work, which I think is everybody who does science, remember that one of the things that we're trying to do is to get students to design and engineer and problem solve. So one of the ways that, you know, once they've generated this list of things on the board of all the things that could change the strength of the magnet, you can focus their design rather, and there's nothing wrong with doing the experiment, but you can focus it differently by saying, how can we design the strongest electromagnet? What things need to be in place to make it the strongest? And you could split it up and have one group look at thin wire, one group look at thicker wire, whatever, and come together and design, or you could have them design, you know, on their own based on the exploration that they did. But that makes it a little bit more NGSS engineering friendly, and still give it structure, because as you know, if you give them a completely open forum, it can descend into chaos and nothing. And so you want to make sure that they're focused with a good question. So asking them to design the strongest magnet, the strongest electromagnet.
If you back up a slide, the questions, or yeah. So when I read, make sure you don't overlap the wires when you wrap around the nail, I'm like, I've done this with students and I know that it works even with them all, like, because kids randomly wrap them up and it works. So I don't know if it would be better to take that off or leave it on, because it made me think, hey, I'm gonna test, does it work better when it's all organized and wound up nicely, or does it work just as well when it's randomly wrapped up? And so it looks like it's stronger when it's organized, which might be why that's written there. But if you're trying to get them to think and to come up with variables that might create differences in strength, you want to leave it off and make them think of it themselves, or does it prompt that kind of thinking because it's there? I don't know the answer to that, but I just thought I would share my frame of
And then to close with and to add on to what Kathy was saying, E says, does your data support your hypothesis? It's very, very important for the girls to be looking through their results, comparing it to what they thought. There's no, penalty in being wrong, but just so that they can have and cite that evidence to support what they said, and then that communication aspect. If they, each group should share what they found. It's very important that the girls are comfortable in sharing and speaking. That's part of our, 21st century skills. And just comfort as they're getting older. Whether it's informal, it doesn't have to be anything that they're standing up in the front of the room, just sitting at their desk, but sharing out with the rest of the group.
Yeah, we also like to put I have a whiteboard in my classroom, obviously. We like to put a data, just like a chart that says who it is, how many paper clips did it hold, and just so that they can kind of gauge where they are in comparison with everybody else.
Yeah, share on the board, everyone writes kind of their data to see, yeah. Okay, any questions with this? Electromagnets?
All right, so we should probably we're gonna take just a little bit of a break so that everybody can go to the bathroom, you can ask questions if you want to. We're gonna move on to the next
Where's the one?
activity unless
Right across the, thank you.